Assalamu alaikum. This is lecture 9, Symmetry Method 1. We are going to derive second equation of Lie symmetry in this lecture. Let's start outlines of this lectures. Lecture are derivation of second formula for the Lie symmetry of differential equation, and then comparison of the first and the second formulation of the symmetry of differential equations, and summary of the lecture. Okay, we know that what is a symmetry generator of a differential equation. You see, this is variation in the H is the given differential equation, and this is variation in the differential equation with respect to epsilon. Epsilon is a continuous parameter. We all know that the bar x's are the new one, while the unbar coordinates are the old one. So these are the new coordinates which vary with respect to the epsilon. So using chain rule, we have this equation. This is change in h with respect to x and change in x with respect to epsilon. Change in h, change in the differential equation with respect to the y bar, change in y bar with respect to epsilon, and so on. So what is partial x bar by partial epsilon? We call it xi. Similarly, partial y bar by partial epsilon is eta, and so on. So we get this equation, and we can write it taking each common. We left with xi partial by partial x, eta partial by partial y, eta 1 partial by partial y dash, and so on. Operate on each equal to 0. This is the first formulation we all know, and we did it in the class. Now we are going to do something for the second formulation. When we are interested in Lie symmetries of a differential equation, H we put here. This will give us a system of partial differential equation. We solve that partial differential equation and get all the symmetry generator admitted by the given differential equation H. Okay, similarly, we all know, we did it in the class, that as an nth order differential equation can be put in this shape, which is given in 3 3 0. The f is a function depend on x y dash up to y in minus 1, and this omega is a function of x y dash y double dash up to y in minus 1. So this function is sort of first integral of this nth order differential equation. This is my symmetry generator extended up to n minus 1th order. What does symmetry generator do with the solution? It maps solution on the solution set This do the symmetry generator do with the solution. Omega is a space of solution and phi is a solution. When you operate the Lee symmetry generator on the solution, it will give me function of the solution. So in fact this generator give map solution and solution, and the operator A, which is the total differential operator, this is the total differential operator. When we operate the total differential operator on the solution, we get 0. So whether we operate it on phi or a function of phi, it will give me 0. This is the total differential operator. And phi alpha is, we can call it first integral or solution of the nth order differential equation. What is the commutator do? Let's see. This is the commutator of the lead symmetry generator, and the total differential operator is defined in this way. Putting the values, we can, x is defined previously over here and a is defined over here. Put this x and a in this equation and collecting the like terms, we can get this. So see, partial by partial x and partial by partial y and partial by partial y dash with some component. So you see this is again an operator like x. This is like x operator. So what the commutator is? The commutator is in fact another symmetry generator. It give me the other symmetry generator which belong to the given algebra. So the what the symmetry x do, that same thing will do by the this commutator. Let operate the commutator on phi alpha, which is first integral or solution of our nth order differential equations. So when you put it here, you will get always 0 because this give me 0 because is a total differential operator operate on a solution. So the total differential operator operate on a solution give me 0. And x operate on phi will give me some function of phi, and again a will annihilate that, so this is again 0. So 0 minus 0 is 0. Okay, so what that mean? That mean that this operator is like the total differential operator. Whether you operate a on f or the commutator on f, I will get 0. What this mean? That the total differential operator and the commutator, and the commutator do the same job. That mean they are some function multiple of each other. What this a do, the same thing will do by this commutator. So that mean this equation hold for some function lambda. Okay, now we are going to compare the left and right side. What is the left side? This is written explicitly in 333. In what is the right side? It can be multiply this with lambda. This with lambda is the right side of this equation. So what are we going here? We are going here to compare right and left side with the help of partial by partial x, partial by partial y, partial by partial y dash. They are independent terms, so we compare like term on both sides. That will give me the first a operator on xi give me lambda. So this is in fact definition of the lambda. Okay, and this is the total differential operator. Okay, so here is that comparison. This is the left side and this is the right side. This is the value of lambda. Is this is lambda? Yeah. So you see the left side of right side of equation 335 explicitly here. So from here what we see, something will cancel. Let's talk about only this one. Eta 1 minus, take a bracket here, d eta by dx, and this will become plus here. So taking minus common, it again minus dxi by dx with a y dash. So this minus this term give me eta 1. So eta 1 minus eta 1 will cancel out. So this first term is cancel out. Similarly, you can see that this thing minus y double dash multiplied with this minus this will cancel out. So what we left with, we left with the last two terms, these two, and omega is y double dash, no, not y double dash, omega is yn. So yn multiplied with this subtracted from this is eta n. So x operate on omega minus eta n equal to 0. X operate on omega minus eta n is equal to 0, which give me x operate on omega equal to eta n. So this is the secondly differential operator. This is the second Lie equation from which we can calculate the Lie symmetry generators and all the Lie symmetries admitted by differential equation yn equal to omega. Why this mode yn is equal to omega is written here? This is for the purpose that we are talking about the nth order differential equation. If it is the second order differential equation, then this will be eta 2. If it is a third order differential equation, then this will be eta 3 and so on. Okay, so this is the second formulation of the Lie symmetry of differential equation. So let's talk about a little bit about the comparison. This is the first formulation. X operate on the differential equation give me 0 given that h equal to 0 itself, and my h is equal to this thing because the nth order differential equation yn equal to omega. So bring omega over here. So yn minus omega equal to 0. That is h. Okay. Now operate x on this h. Here is x. Here is x. So when you operate x on eta n, on yn, I will get eta n. So this is x operate on yn give me eta n minus x operate on omega, and that is equal to 0 because x operate on h equal to 0. So what I get, eta n minus x operate on omega is equal to 0. That is in fact the second formulation of the Lie symmetry. So in fact both are equivalent. The first formulation and the second formulation, this is the first formulation and this is the second formulation, both are equivalent, they are the same thing. So what we did in this lecture, we derived the second formulation of the Lie symmetry of differential equation. This is nth order differential equation, can be put in this form, yn is equal to omega, and can be put in this form as well. This is the total differential operator, operate on a function of x, y dash up to yn minus 1 will give me 0. This is the first integral, and differentiating that first integral again one time, I will get nth order differential equation. So all these are equivalent. This is my symmetry generator. I am defining extension of the generator in this equation. This is the mth extension of the generator. This is the first Lie symmetry equation, and this can be put in our equivalency this thing because this symmetry, this commutator and A do the same job, so A operate on integral, first integral, or this operate on first integral, both will give me 0. So whatever we did here is equivalently here. So that is the end of sorry, I think I miss one thing, and that is the second symmetry equation. The second symmetry equation is missing over here, but let's see in the book. Okay, this is the so that's all. If this is whole, then this equation also whole. But the second formulation is in fact x operate on omega equal to eta n. Students are advised to solve this exercise 3.5, which contain 4 questions, and the last question is very important. These 3 are easy, but the last question is an important question. The student have to try to answer this all these, but particularly this question number 4. Thank you and take care.